Prahlad, we wanted one.
The talk.
Okay, welcome everyone. We are very happy to have Ramya here. So Ramya is visiting from IMSC. She's around this week. You should find she's in the visitor's office next to my office. Ramya did her PhD at IIT Madras and moved to IMSC after a few years at CNI. She was here during most of COVID, I guess. For her postdoc, and while she was here, we worked on some things where we tried to show that proving low box is hard, and we only had limited success. Because it's why.
I must thank Raghuvansh for inviting me here. The last time I gave a talk, formal talk was in 2019, and I reused some of the slides, but I can see some new faces, so I think it's okay. So I'm going to talk about arithmetic circuits yet another time. We are already attending the talk. That time also I spoke about arithmetic circuits. This is about planar arithmetic circuits, and it's a joint work with Pratik Shastri. He's a PhD student at IMSC. So, if there is anyone in the audience who has not seen an arithmetic circuit, it's a model for computing polynomials. So, most of this talk will be talking about computing multivariate polynomials. So, that's n variables, let's call them x1, x2 to xn, and these variables form monomials, and it's a polynomial where the coefficients come from a field. You can think of reals, complex numbers, and so on. So one model to compute polynomials is that of arithmetic circuits, like the picture on the right. So it's a directed acyclic graph where the leaves are labeled by either variables x1, x2, and so on, and constants from the field. And internal gates here are labeled by either addition or multiplication. And every gate, let's say, has spanning 2. And if it's labeled by some gate, it's going to compute the sum of its children, and if it's labeled by product, it's going to compute the product of its children. And there are many gates. One of them is designated usually as the output gate. And the polynomial computed by the circuit is the one computed at the output gate. So here it computes x1 square plus 3x2 plus 2. Sometimes even edges are labeled by constants to allow for scalar multiplication. So if this edge is labeled by, let's say, alpha, then the value on this wire is alpha times whatever is computed in this. And there are some parameters that are usually associated with an arithmetic circuit. One is the size of the circuit, which is the number of vertices in this graph, which tells us how many arithmetic operations are needed to compute this polynomial. And here this graph has size 4, and depth, which is the length of the longest path from the leaf to the root. So this graph has depth 3. So there are many ways to compute a polynomial. For example, if you wanted to compute the polynomial 1 plus x1 plus x2 plus 1 plus xn plus x1 x2 x2 x3, all possible monomials, then you can sit and write it down as monomial by monomial and draw a circuit. But a cleverer person would possibly write something like this: 1 plus x1 times 1 plus x2 xn minus 1. This computes all possible monomials of all degrees. And you have only like n minus 1 multiplications. Now the question is there a cleverer way to compute this? And this turns out to asking if there are several ways to compute a polynomial, what's the best way to compute it? Or in other words, can you come up with a polynomial on n variables such that no matter how you try to draw it as a directed acyclic graph, the number of operations that you will need is super polynomial in n, something like n to the little omega of 1. Can you construct such a polynomial? And by explicit, we mean that in some sense, if you give me the monomial, I should be able to tell you what the coefficient is reasonably efficiently. So if you've seen a bit of complexity, the coefficient should be computable in the class star p/1. If you haven't seen, it's fine. So the whole goal in algebraic complexity is to find a polynomial, an explicit polynomial, on n variables such that any circuit computing it requires super polynomial size.
It requires some amount of degree also. Otherwise, you can just have very large degree or something.
So n variable polynomial of degree polynomial. That's right. So n variable polynomial degree polynomial such that any circuit computing it requires n variables. So this has been around. This question has been around since 1970s. So no need to say how far a progress has been made. So if you look at this polynomial, x1 to the n plus x2 to the n plus xn to the n, Baur and Strassen in 1983, they showed that the number of product gates you need to compute this polynomial is n log n. So any fan-in-2 circuit computing this polynomial must have size at least this much. So the goal roughly is like n to the little omega of 1, and the current best is n log n. So this has been the current best. It's an embarrassment in every talk like this, but this time it's much better. So we have some progress.
Not if there are Boolean people in the audience.
So we should be proud of it. So there are some things to note here. This works over any field, and the individual degree of every monomial here or every variable here, the individual degree is n. X1 to the n, x2 to the n, xn to the n. And there's also a nice circuit computing this polynomial. So this x1. So if there are Boolean people in the audience. So this computes x1 to the n. N such lines. Computes. So this is the circuit. It uses repeated squaring and it has size like n log. So there's a matching upper bound. Okay, so we haven't made much progress on this question, probably because we are allowing like repeated squaring, which is a lot of power. So maybe if we forbid that power, then can we get better lower bounds? So if you restrict the underlying graph to be a tree, it can improve better lower bounds. That's the question. So if you forbid repeated squaring here, then what happens? So then it's easy to see that where the underlying graph is a tree, such circuits are called formulas. And it's easy to see that any formula computing this polynomial must have size omega n squared. So this is because the underlying graph has to be a tree, then the out degree has to be 1. And you want to compute x1 to the n, so you need to have n leaves labeled by x1, n leaves labeled by x2, and n leaves labeled by xn. So there are n variables, each having individual degree n. So you need to have n squares. So it's a lower bound, but it's not very interesting because it says that the individual degree is this large, and you need to have at least so many degrees. So a natural question you would want to ask is, can you find a polynomial with low individual degree such that any formula computing it must have quadratics? So Chatterjee, Kumar, Shiendo, they showed a quadratic lower bound on the size of any formula computing an explicit multilinear polynomial, meaning the individual degree is just 1. But the total degree here is 0.1. So the total degree is a function of n, but the individual degree is 1. It's a quadratic lower bound. Okay, so that's where we stand. So all of these are size lower bounds, so lower bounds on the number of internal gates. The other parameter we had in mind was the depth. So a natural question to ask is, if you restrict the depth, what can you say? And in a breakthrough in 2021, Nimai, Srinivasan and Tavanna, they showed a super polynomial lower bound for constant depth circles. So the question is sort of partially resolved if you restrict the depth to be a constant. So this is the progress we have made compared to the previous talk. So, from 2019.
So is it a result of Chatterjee et al.? Is it an affine projection of the previous lower bound, or is it a complete, the specific example for which they prove the lower bound?
It's the elementary.
It's just elementary.
It's an n point model.
Yeah.
But it requires the characteristic of the field to be greater than the degree. It's easy n point model. So it's a multilinear polynomial, but the total degree is function of n.
Okay.
So now you can ask, can you remove that restriction of total degree being a function of n, where the total degree of the polynomial has to be constant. So the question is, can you find an explicit polynomial of constant degree such that any circuit computing it is n log n? So in some sense, this Baur and Strassen's lower bound is for a polynomial that has individual degree n, or total degree was n. So can you prove a similar bound for constant degree polynomials? And so this still remains open. We try to solve a very special case of this problem. So for constant degree polynomials, what is the best we know? It appears that for circuits we know nothing. Even the Baur and Strassen lower bound seems to be open. But if you restrict the underlying graph to be a tree, that is a formula, then you can construct a degree 3 polynomial on n variables, such that any circuit computing it requires superlinear size, like n to the 3 by 2. So there is some improvement when you move from circuits to formulas. In circuits, you know nothing. So circuits are best lower bound currently we have is like omega n. There are n variables, so you have to use all the n variables.
You can actually get to n to the 2 minus epsilon for the second one. If you let degree be 1 over epsilon.
For any epsilon.
For any epsilon. Any epsilon greater than.
So now the other analogous thing is what is the case of constant depth. For constant depth, you can prove like lower bounds of the form n to the 1 plus omega 1 by r, where r is the degree and the depth. Right? So for any constant, you can find an explicit polynomial on n variables with total degree order r, and such that any depth r circuit must have so much size, n to the 1 plus. So this remains largely open. For formulas and constant depth, we have some reasonable limits. So now getting to what is planar circuits. So planar arithmetic circuit is an arithmetic circuit where the underlying graph is planar. So there are no edge crossings. So any tree is a planar graph, which means that every arithmetic formula is a planar arithmetic circuit, and any planar arithmetic circuit is a circuit. So now the question is, okay, how far are planar arithmetic circuits from circuits? If you are given a fan 2 circuit, like this, something like this, which has size S, computes a polynomial f. So this is an example of a planar circuit, computing the polynomial x1 to the n plus x2 to the n plus xn. There are no edge crossings here. So given a circuit, can you sort of planarize the circuit? Right? Can you construct an equivalent circuit? And I mean equivalent another circuit that computes the same polynomial but is planar. This can be done with quadratic blow-up in size. So what you do is, so the given circuit may not necessarily be planar, so there will be edge crossings. So somehow we need to eliminate these edge crossings. So at every crossing here, so there are 2 gates here and there are some 2 wires. So whatever is on this wire must reach this gate and so on. So there is an edge crossing. So this crossing can actually be eliminated by attaching a small gadget. So this gate computes f plus 0, this gate computes f plus g. You want g to reach this wire, so you need to subtract a couple of. This gadget has constant size, just like 5 vertices and few edges. So at every edge crossing, you can eliminate this crossing by pasting this circuit. And the number of crossings in a circuit is like the number of edges choose 2. And any planar graph has roughly like 3n minus 6, then is the number of edges. So s square will be the bound you get after you planarize this circuit. You can construct another circuit that computes the same polynomial but is now planar. But the blow-up in size will be from s to order s square, the quadratic. You have to be slightly careful while planarizing, in the sense you have to fix an embedding of the original circuit, and you must paste this gadget in a neighborhood such that there are no other vertices or edges. So you have to be slightly careful, but it's not hard. And this was already known in the Boolean setting. We know how to planarize Boolean circuits. We just observe it. It also works in the arithmetic. So what does this tell us? This tells us that if we are able to show an explicit n-variate polynomial such that any planar circuit computing it has size like omega n power 4, then it would directly translate to a quadratic lower bound for circuits. And thankfully, we don't show any such, right? Our results are really weak. So there's one property that we may need is that in any planar circuit, you can always assume that the fan in and fan out of every gate is at most 2. So if it has fan in R and fan out R, then you can attach a complete binary tree with R leaves, and you can convert it into another planar circuit that computes the same polynomial with only some constant blow-up. So this means that the separation here, if you've seen some separations in complexity, cannot be more than quadratic. We come to that. Okay. So planar's arithmetic circuits are, we haven't seen anybody study this, but planar Boolean circuits are well studied. So Lipton and Tarjan, they were the first to come up with the planar separator theorem, if you know of it, and one well-known application of the planar separator theorem is lower bound for Boolean circuits. So Lipton and Tarjan in 1980, they showed quadratic lower bounds for read-once planar Boolean circuits. So what read-once planar Boolean circuit means is that every variable appears as a leaf only once. It's read only once. For example, this is a read-once planar arithmetic circuit. x1 appears only once as a leaf, x2 appears only once as a leaf. But this lower bound is for multiple functions, in the sense that they compute n functions and they say the size has to be at least n squared, which is in some sense weak. So you would want to say that there is one Boolean function on n variables such that the size is quadratic, and that's what Savage did as an improvement in 1981. An n square lower bound for read-once planar circuits computing one explicit invariant. So, but these are read ones. So how do you get rid of the read ones restriction? And Turan showed that you can, so the lower bound has sort of degraded when you get from read ones planar Boolean circuits to planar Boolean circuits. There they were able to show an n square lower bound, here is only n log n, but it's an explicit Boolean function on n variables. So all of these results are well known in the Boolean setting, it's just that people didn't study this in the setting. It's sort of natural in the sense that if you want to show formula lower bounds, maybe this is one way to do formulas as planar graphs and exploits this planar. So all these lower bounds use variants of the planar separator theorem. We'll see what the planar separator theorem is, theorem C. And if you've done some bit of complexity, then one natural first attempt is to try and arithmetize this Boolean lower bound and see what you get. If you try to arithmetize this, there are some basic troubles. So the first thing is all of these Boolean lower bounds sort of use the fact that on any wire, you can see only two possible values, either 0 or 1. But this is not true when you look at arithmetic circuits, because over finite fields, this wire can carry any value. And the explicit Boolean function, if you try to arithmetize this, you've seen arithmetizing Boolean functions, you will get a polynomial of degree n. It's linear degree, and it's not explicit in the sense we want it to be. Like if you give me a monomial and ask me what this coefficient is, I have no idea what the coefficient is.
So between Savage and the Lipton-Tarjan thing, I mean, is there is the final n-variate Boolean function? I don't know. Is the analog something like Baur and Strassen, the standard? You go from a single polynomial to computing derivatives. Is there some analog of that happening there?
No. So this is, I think, Boolean convolution, and Savage, I think, is based on super concentrators.
Oh.
Even this is actually, so in Turan's result is this explicit Boolean function. You get it from a linear size super concentrator. So it helps. So this natural thing of going from partial derivatives, using partial derivatives, get from like n functions to one function. That's not how it works.
Oh, that's not how. Okay.
So you can't potentially arithmetize these directly and get lower bounds. So you have to do some more tricks, which is what we do. All analogous results for Boolean with Boolean replaced by arithmetic. Okay. So we should digress a bit and look at constant degree polynomials, and we'll come back to planar series. So what is a bilinear form? So a bilinear form is a polynomial of this. So you have two n variables. One is set of n variables y1 to yn, and then there is a matrix A, which is n cross n, and then there is a column vector x1. So it's y transpose ax. So it's a degree 2 polynomial. So x and y are vectors of variables, and A is an n cross n matrix. And a bilinear form that is defined by this matrix is a polynomial of degree 2 y transpose x, which is what you get if you multiply this out. Polynomial of the form sum over all i's, j's, aij, yi, x. So this is what we call a bilinear form. So it's a special case of constant degree polynomial. This polynomial is degree 2 on 2n variables. So any bilinear form, if you open this out and draw a circuit computing it, you can see that this is actually a tree and it has size order n square. So the best lower bound we know is any circuit computing a bilinear form must have size omega n. There are 2n variables, so you must use all the variables. So a natural question to ask here is, can we say, can you construct an explicit bilinear form such that any circuit computing it requires size omega n log n? Maybe n square. Order n square is the upper bound, so you would expect something like that. And we need to also say what is explicit bilinear form. So explicit in the sense that there is a polynomial time algorithm that takes n as input and outputs the entries of the variables. We call such a bilinear form explicit. And explicit bilinear forms were studied by Nissan and Peters. So this open question still remains to construct an explicit bilinear form such that any circuit computing it requires size n log n. So if you think a bit about this, this is a special case of the question we asked earlier. Is there a constant degree polynomial such that any circuit computing it requires n log n? So now I'm saying not a constant degree polynomial, but is there a polynomial of this form of degree 2 such that any circuit must have superlinear. Okay, so now it's like an anthology. We have made the pieces, now I should piece them together. So what we are able to show is that there is an explicit bilinear form such that any planar arithmetic circuit computing it has size omega n log n. So what is the M here? So M can be any totally regular matrix. So totally regular matrix is a matrix such that if you take any square submatrix, it has full rank. Such matrices are called totally regular matrices. So one example of a totally regular matrix is a Cauchy matrix. Like the ijth entry is 1 by ai minus bj. So a1 to an, b1 to bn are like distinct numbers. And so this any submatrix of a Cauchy matrix is a Cauchy matrix, and you can use this to argue that it's totally regular. So you pick any square submatrix, you have full rank. Such a matrix is called totally regular. So if you fix any totally regular matrix M in the place of A and look at the bilinear form Y transpose MX and try to compute it using a planar arithmetic circuit, it must have size at least omega n log n. So that's what we try to show in the rest of the talk. So over infinite fields, you need 2n distinct entries. Otherwise, you will try to divide by 0. So over large fields, explicit totally regular matrices exist. Over finite fields, we do not know of any construction of totally regular matrices at the moment. So this is a lower bound. A natural question to ask is there a matching upper bound? So there is no known construction of a totally regular matrix such that any planar circuit, such that there is a planar circuit computing it, this bilinear form and as size order n log. So we are just able to show the lower bound. There is no known upper bound as far as we know.
What if you drop the planarity from restriction? Then is there a Cauchy matrix for which you can get n log n?
Yeah, there is.
You
can construct it from a super concentrate. We'll see that then.
Okay.
So from any super concentrate, you can construct it totally regular.
Okay.
But it has some caveats.
Okay.
Is the DFT matrix going to be
I think there are 2 cross 2 submatrices which are actually not full. Yeah.
So over finite fields, we do not know of a construction of totally regular matrices. We try to do this using codes, but it seems hard. We can get almost totally regular matrices from codes.
What does almost mean?
Like if you pick n by 10 cross n by 10, then
All big minors.
big minors are
That's
full rank, but
what
if you
DFT.
Yeah.
But if you take small enough minors, then this does not hold, and the proof requires large enough minors.
What about the Pascal matrix? This is where the ijth entry is I plus j choose I.
It probably has a lot of zeros over small characters.
No, he's saying I plus j choose.
I plus j choose I.
Oh, over small characters.
No. Assume zero characteristic.
But that's triangular.
No, I plus j choose I.
I mean, you look at the whatever, this corner of no.
Right.
Yeah. The DFT matrix is an example of a bilinear form which is in n log n.
Yes.
Because of the FFT.
But here you require M to be totally regular, which is
Oh, sorry, that's not planar by any stretch.
No. Oh,
Yeah. Yes.
it's not totally regular. Okay, so this is
That wasn't even common.
so this seems open-ended. So similar to the Boolean setting, you can also restrict the circuit to read every variable at exactly once, like this. You read once planar circuit polynomial. And you can ask if you restrict now the circuit to be read once planar can improve the lower bound. So then you can get from n log n to n square for the same bilinear form Y transpose mx where m is totally. So in this talk, we'll try and prove this statement that any read once planar circuit computing the bilinear form Y transpose mx where m is totally regular must have size omega n square. This is because the proof is easier to demonstrate. So the technique sort of carry forward. There are some changes that you have to make, some surgeries, but this is easier to demonstrate. Okay. So to get to the proof, we need some ingredients which we put now. So if you look at the way a bilinear form is built, right, it's a polynomial of the form, every monomial is like xi times yj or yj times x. So in the circuit, you may be intelligent and you may want to compute things like x1 square, x2 square y, x3 square y3. But no matter what you compute, these things have to be cancelled before they reach the root. Because these things are not there in your output polynomial. So in that case, why do you compute? Don't compute. So bilinear circuit is a circuit where in any product gate there are exactly two children. One of them computes a linear form in x variables, the other computes a linear form in the y variables. So in some sense, no product multiplies an x with an x or a y with a y. Right? And every product gate has exactly two children. So if the circuit has this structure, that every product gate multiplies a linear form x with a linear form y, you call that circuit a bilinear circuit. And what Nissan and Peterson observed is that any circuit can be bilinearized with constant block in size. So if you start with a circuit of sizes that computes a bilinear form, then there is another circuit where every product gate has this property and computes the same polynomial as the original circuit, but now there is a constant block in size. So this is nice in the sense that now if you want to prove lower bounds, you can work with bilinear circuits and the lower bound will directly translate to general circuits. Now, you can ask, so for bilinear circuits, we currently don't have any lower bounds. It's like omega n, the same situation. There are two n variables, you have to read variables. So now I can try and restrict this bilinear circuit to say that the underlying DAG has to be a tree. You will get a bilinear formula. So bilinear formula is a tree, the underlying graph is a tree. Additionally, for every product gate, you have two children, one computes a linear polynomial x, the other computes a linear polynomial y. Now you can ask, can we say better than omega n lower bounds? Nissan and Peterson showed that you can get superlinear lower bounds for bilinear formulas, right? Computing y transpose mx, where m is asymptotically regular. This has been improved from n log n to n log square n by log n by Radhakrishnan and Kashmir. So that's the status for bilinear formulas. Now, if you look at this statement here, then what we are able to say that if you prove lower bounds for bilinear circuits, that will directly translate to lower bounds for circuits, because circuits can be bilinearized. Now we have a lower bound for bilinear formulas. The question is, does it directly translate to lower bounds for formulas? It would translate if formulas can be bilinearized efficiently. So if this statement holds with circuit replaced by formula, unfortunately we do not know if formulas can be efficiently bilinearized. So this does not say anything about formula complexity of bilinear forms.
But this question of whether formulas can be bilinearized, this may be more approachable than the question about, because we already know formulas of logs and log square and all. So all we need is to prove this lower bound for a polynomial or a bilinear form that has a small circle. Is that right?
To answer this question in the negative?
Yeah. We already know lower bounds. All we need is an upper bound.
For a bilinear form.
For a bilinear.
Yes, that's right. You have quadratic lower bounds for formulas. So if you can do upper bounds for bilinear forms, then
Yeah, and I actually went Radhakrishnan Kashmir. So that's for a supercomputer of some kind.
it uses a depth to supercomputer.
Yeah. So if for that supercomputer we could get a circuit of linear size, for instance, that would give us separation.
Yes. So these bounds above do not imply formula lower bounds for bilinear forms. And if you look at the main statement here, this says that any planar circuit computing the bilinear form must have size omega n log n, and any formula is also a planar circuit. So you have a superlinear lower bound with the formula complexity of bilinear forms without bilinearizing formulas. I mean, this question we do not know currently, but the answer is yes or no. Okay, so I think there are many models like formula circuits, planar circuits, bilinear circuits. I already opened a gazillion of terms. So I hope it's okay. Yes. Okay, so this is the statement that we need to prove. Any planar circuit computing y transpose mx, where m is totally regular, must have n log n elements. So how do you prove this? So we'll do this in two steps. So the first step is, so circuits we know how to bilinearize, formulas we do not know how to bilinearize. It appears that planar circuits can be efficiently bilinearized. So if you start with a planar circuit of size S, that's called the circuit field, it computes a bilinear form. Then there exists another planar bilinear circuit with only constant blow up in size that you can construct that computes the same polynomial f. And if the original circuit is read once, meaning every variable appears as a leaf once, then this new circuit will also hold that load. We will not touch the leaves in this process. And the next step now is you can now work with planar bilinear circuits and say that any planar bilinear circuit computing this bilinear form must have size n. So these two statements put together will give this. But as I mentioned, we'll see the read ones case, which is a stronger lower bound n square because it's easy to demonstrate. Okay, so the main ingredient in all these proofs is the planar separator theorem. So given any planar graph, you can find a small set of vertices, roughly like root n is the number of vertices in the original graph. And if you remove these vertices, your original graph will be partitioned into two disjoint subgraphs. That's what the planar separator theorem says. And the size of these two disjoint graphs will roughly be like 2n by 3. So given any planar graph G and also a weight function, so for every vertex you need to give a weight which is non-negative and at most 1. And the sum total of the weights is at most 1. Then you can find the partition A, B, C of the vertex set such that like, the sum of the weights in A as well as B is at most 2/3. And this set C, which is called the separator, has roughly like a root V many vertices, and there is no edge that joins a vertex in A with a vertex in B. So any edge from A to B, any path from A to B or B to A should go through a vertex in C. So this proof is actually constructive. In linear time, you can find this partition, A, B, C. Maybe I should draw something.
So, yeah, the button is not working.
I'm not going to do anything. So your original graph was actually a circuit. So there were gates saying plus, minus, leaves were all labeled by x1, x2. Now some of the gates going to A, some of the gates going to B, some of the gates going to C. Okay.
So here when we are talking about separator, we don't care about directions and stuff, right?
No.
Okay.
So you look at underlying undirected graph and then apply the things. But we need to apply it, so let's do it. So the statement we want to prove is a quadratic lower bound. So for the contrapositive, let's assume that there is a planar bilinear read-one circuit that computes this bilinear form and a size little of n square. So you have an underlying graph. Now we need to apply the separator theorem to it. So I need to assign weights to all the vertices such that the sum of the weights is 1, at most 1. So we have two n variables, x1 to xn and y1 to yn. I'll give each of those leaves equal weight, like 1 by 2n, and give 0 to all the other vertices. So the sum of the weights is at most 1 now. And you apply the planar separator theorem, which will give you three parts, A, B, C. Like it's here. And the size of the separator is like little of n, because the original circuit has little of n square vertices. Is that okay? I just applied the planar separator theorem. We assign weights appropriately. So now from this planar separator theorem, we know that the sum of the weights of A and B has to be at most 2/3. So the number of inputs mean x1 to xn and y1 to yn, in each of these parts can at most be 4n by 3. Because each of these got weight 1 by 2n, and the total weight has to be at most 2 by 3. Right? Yeah, so this proof is like an exercise. We would do what you would do. So if you look at A, B, C, totally, so it's a graph. So the underlying thing was a circuit. So there were things like this. X1, Y1. Maybe X size here. Some product fed into another product. So if you look at A union C or A union B, one of them need to have at least n by 2 x inputs, because there are totally n variables. So let's assume that A union C has at least n by 2 x inputs. So A alone must have had n by 2 minus little of n, because C had size little of n. That's the maximum number of x variables that can be there. Okay. So A must have had at least some number of x inputs. Let's say this is like 5n by 12. Okay, so some x inputs are in A, but at least 5n by 12 x inputs are in A. So now you know that the total number of inputs in A were at most 4n by 3, of which 5n by 12 were x. So the remaining had to be y variables, which is some 11n by 12. Now there are totally 2n y variables, of which some of them are in A, the rest have to be in B. So we did some calculation using this, and we said that, okay, so there are three parts A, B, and C. A has at least so many X inputs and B has at least so many Y inputs. The rest are distributed across A, B, C. You have no idea. So there are two variable sets X prime, Y prime.
Sorry. So they can't lie in C.
They can, so there's a loss, but there's something there.
There's a loss here, something.
Oh, it's sublinear. Because I thought the C is little one, so
So with little of N,
Sure.
so I just put in
yeah, okay.
some number to get 5 and 5.
Yeah, okay.
Some of them can be in C, but at most little of N.
Okay.
Okay, so you have two sets of variables, X prime, Y prime. Each of them have size roughly like N over 13, like omega N. So the minimum of this is N by 13, such that all the variables in X prime are contained in A and the remaining variables are contained in B. So this is how the picture would look like. So you have A, you have B, you have C. This is a representative image. Your original circuit may not be like this. But there is a set of X variables inside A and there are a set of Y variables inside B. And then there are a bunch of other variables which are in green, which you don't. Now this circuit that we started with was read once. So these X prime variables cannot appear here and these Y prime variables cannot appear here. Okay. So maybe you should try and complete the argument. So there are some variables in X that are outside X prime and some variables in Y that are outside Y prime. You set all of them to 0. So in this bilinear form, some of the yi's now became 0, some of the xi's became 0. Your original circuit was computing Y transpose mx, where m is totally regular. That's the assumption that we started with. So now some of these entries are 0 and some of these entries are 0. So some columns, some rows are gone. So after you set it to 0 in this circuit, it will still compute a bilinear form, but it computes something like Y prime transpose M prime X prime. Like some of them have vanished. Where M prime is N by 13 cross N by 13 matrix because that's the size of X prime. Now, we know that M was totally regular and M prime was a minor of M, so this had to be totally regular. I mean, this had to have full rank. So rank of M prime is N by 13. So that's what we have. So now we need a contradiction. The contradiction is that we'll show rank of M prime should be little of M. So this is a contradiction. The original assumption that we started off with. The only assumption that we started off with was the size of this is little over square, which is 1. Okay, so I'm going to do something about bilinear circuits, which is not very hard to prove. So the original circuit we assumed was read once, planar, bilinear. We have used read once property, we have used planarity, so we need to use bilinearity. So in any bilinear circuit, if you look at the output gate, so the output gate actually can be in A or B or C. We don't know. It's in one of these things. So let's assume it's in A. Assume it's without loss of planarity. In this image, I have put it in A. You can always construct a bilinear circuit where the output gate is a linear combination of all the product gates in this circuit. So output gate is a linear combination of product gates in A, product gates in B, product gates in C. So this is something you have to believe me on. We'll try to see a short proof if there is time. So now we need to somehow argue that the rank of this M prime, after you substituted some of the y's and the x to 0, must have low rank. Low is little of n, and then we get a contradiction. So we need to understand linear combinations of product gates. So first let's understand one product gate. That's not clear. Linear combination is more advanced. So let's say G is a product gate and it's in this partition A. So the circuit was bilinear, so it had exactly two inputs. One computes a linear polynomial in X, the other computes a linear polynomial in Y. So if you step back, there were X prime variables here, Y prime variables here. We set everything else to 0. And one of the children of this product gate depends on Y variables. And there were no Y variables here. I set everything to 0. The only Y variables are here. So if this computed a linear polynomial in Y, it must have somehow come through C. There is no other way because there is no edge from B to A that does not, there is no path from B to A that does not go via C. Since A has no Y prime variables and there are no edges from B to B, B to A, this linear form must have come through C in English, but we need to say what that is in math. So in math, this would mean that this linear polynomial here can be expressed as a linear combination of m many linear forms in the y-prime variables where m is at most c. So this is something you can prove inductively. Requires some work, but it's not very hard. So it's just
So you kind of see, you see as a circuit with things coming from B, like whatever. B
yes. So this is for a product gate in A. Now, if you look at a product gate in B, you can apply a similar argument. So if a product gate in B would have two inputs, one computing a linear polynomial x, the other computing a linear polynomial y. The y variables it can pick from itself, but the x variables must have come from A through C. So a symmetric argument you can apply. So now you can do this for a linear combination of product gates. The linear combination of product gates would look like this, where each GI is a product gate. What you know is this GI can now be written as a linear combination of m many linear forms. So you get this expression. So any linear combination of product gates in A can be expressed as y prime transpose n1x, where the rank of this is at most C. So a rank of linear combination of product gates in A is at most C, B is at most C, and C also is at most C because C has anyway alternative C matrix. This is the math version of saying these things must have come through C. So if you look at the output bilinear form, it's a linear combination of product gates in A, B, and C because the original circuit was bilinear. So by subadditivity of rank, you can say that the rank of this matrix is at most 3 times the cardinality of C, and C will be low. So the rank of m prime is low of n, which is a contradiction. The only assumption we made was that the origin. So you got that C was little of n because the original graph had size little of n square. That's the only assumption which is incorrect. Okay. So there is one. This is the second step in the this one. So what we've shown is any planar bilinear circuit for F must have size n log n. So this step that we did here crucially relied on the fact that the circuit was read once. Otherwise, you could never do this because if there's a product gate here, then we can also find its x variables here. You don't have to come from here. So you have to use more sophisticated separator theorems when you get from read ones to non-read ones. You will use a more sophisticated separator theorem due to theorem. But that's the only place you have to change. Everything else is.
Also, here the proof works if you don't have totally regular, you only have that almost, because you only need to have
n by 13 cross n by 30. So now if you use more sophisticated, then you will roughly need like n to the 0.96 cross n to the 0.96 matrices after full rank. Then we don't know the final piece out of such a matrix. That's it. Okay, so what we are yet to see is how to bilinearize a planar circuit. So we don't know how to bilinearize a formula, we know how to bilinearize a circuit. So the proof of bilinearizing a planar circuit is exactly similar to bilinearizing a general circuit. But let's just go over it since we haven't seen it. So let's consider some gate in the original circuit. So what do we want to do? You're given a planar circuit which computes a bilinear form. I want to construct another circuit which is planar and also has the property that in any product gate there are two children. One computes a linear polynomial x, the other computes a linear polynomial y. And I should have only a constant block in size. So if you pick any gate B and look at the polynomial computed it is at this gate, it may have a x linear part, a y linear part, a bilinear part in xy, so monomials of the form xi yj, and then there will be some rest, which is like x squared y cubed, and so on, other monomials which you want to sort of get rid of. So you can inductively construct this bilinear circuit. For every gate in the original circuit, we introduce 4 gates. One computes a constant term, the other a linear part, x linear part, y linear part, and bilinear part. So if you have seen homogenization kind of arguments, this is exactly similar. So if you have a leaf labeled xi, then you put bx equal to that xi, rest of them are 0. If the label is, it should be yj, then you set the y linear part to yj, rest of them is 0. If it's labeled by a constant, then the constant part is 0. Now you need to do this bottom up. So for leaves we have done, now you need to do this for some gate. So the thing to use here is that in any planar circuit, the fan in and fan out is at most 2. Right? So the fan in is exactly 2 here. This is like not very hard. So the constant term of this polynomial must be the sum of the constant terms of these two. So for every gate, you sort of add this box with 4 gates and then plug in the wires appropriately. But now the thing is you will find some crossings in this process, which you will have to eliminate using crossover gadgets, which we first saw. You need to argue that the number of crossings is small, but that is because the fan in and fan out is 2. You start off with the number of crossings here will be small. Similarly, you can do this for a product gate as well. So, but for a product gate, you need to be slightly careful in the sense if you look at the bilinear form of FB, it can be picked up from the x-linear form here, y-linear form here, or the y-linear form here, x-linear form here, and so on. So, you need to write an expression and similarly draw a circuit which will not be planar, and then you have to eliminate the vertices. You have to be a bit careful in the sense for every vertex here, you are adding a box of vertices. So if you think at it, you need to zoom into the embedding as much as possible so as to not touch any other portion, and then add these 3 gates. And then add edges accordingly, like correctly parallel to the original embedding. So you need to look at the original embedding of the circuit. It's not like you can do things as you wish. Okay, so this part just holds for like planar circuits. It's just the first part. If you want to show it for planar but not read ones, you have to use sophisticated separate. So this is what we've done so far. Like we've tried to show that any read ones planar arithmetic circuit computing by transpose mx, where m is totally regular, has such lines. So we introduced some like models, circuits, planar circuits, read ones planar circuits, formulas. So now we need to see are there any kind of separations between these. Oh, so these things are not hard. So maybe we should define something called a super concentrator or n super concentrator. So n super concentrator is a graph where you have n inputs and n outputs. And it's super concentrator in the sense, so let's call this IN. So if you pick any subset of k vertices here and k vertices here, for any k, then you'll find k vertex disjoint paths from these sets of inputs to these sets of outputs. Then such a graph is called an n super concentrator. So if you're seeing this definition for the first time, you would expect that any such graph should be dense. Because I pick any set of k inputs and k outputs, then there will be k vertex disjoint paths, which sort of means that there must be many edges to it. Or if there were just n lines, clearly this property doesn't fit.
It's important that you only choose the subsets, you don't choose the ordering.
Correct.
Yeah. In the sense that once you choose k here and k there, there is some specific noise that will happen, but
you don't specify this to this.
yeah.
Between these, so it's between and between.
Yeah.
From to. So this is called an n super concentrator. You would expect that any super concentrator must be dense, but contrary to the expectation, for every n, there exists n super concentrators of linear size. So linear size meaning linear many edges. Just with order n edges and depth poly log n, you can ensure that for any choice of k inputs and k outputs, there are k vertices joint paths. And it's explicit in the sense that there is an algorithm that can actually output the graph in polynomial time. So now we want to find a separation between circuits and planar circuits. One thing we have shown is that if your planar circuit computed y transpose mx where m is totally regular, then the size must be n log n. So we want to use that total regularity. So what Variant observed is that if I start with an n super concentrator here, and there are inputs here, n inputs, so I can put x1, x2 to xn. I mean, label the n inputs as x1, x2 to xn, and every other gate as plus. So there will be n linear polynomials computed at the output, L1, L2, L3, so on to Ln, because everything is an addition gate. And the inputs are all labeled x1 to xn. Now there exists a weight function where you can assign weights to these edges, right? Such that the linear forms L1 to Ln computed at the output gate form rows of a totally regular matrix. So this is what Variant does. So from an n super concentrator, you can get a totally regular matrix. There exists a weight function. So this also answers this. So if you look at it, this means that there is a circuit. You have assigned vertices as plus and then the leaves are all labeled x1 to xn.
What is, so I know the Variant, immediately after the 77 paper, he had constructed a super concentrators and linear size super concentrator. So what is Strassen's contribution? He gets the
Depth
depth
is
to,
poly log log n.
that is, original variant was log n depth.
Yeah.
And this
I
is
think it was poly log n. Maybe log n.
log n depth will get you. I think if you have an expander, you can get log.
Right. From log n to poly log n.
Log n is Strassen's. Okay.
So what this tells us is over infinite field, there exists a totally regular matrix such that Y transpose Mx has order n size circuit. So you look at this circuit, put x1 to xn in the leaf, every other gate is plus. You will have computed L1, L2 to Ln here, multiply each of them, this by Y1, this by Y2, this by Y3 and so on, and add them up to compute Y transpose Mx. So this is, you have to adjust this though. You have to put plus gates and multiply by corresponding Yi's. You will get a linear size circuit computing Y transpose Mx, but we have shown that any planar circuit requires n log n size. Now the catch here is that what variant observes is that over infinite fields, you can see that there exists a weight function. We don't know how to get this explicit. There's an explicit way of constructing the weight function. So this does not give an explicit separation between circuits and planars. It just tells you that there exists a bilinear form, which can be computed by linear size circuits but requires superlinear. Superlinear is n log. So finding an explicit separation between circuits and planar circuits still remains. That's because this construction of totally regular matrix from superconcentrator is not known to be explicit. Okay, so now you can ask, so that if you look at this picture here, it tells there's some separation here, but then there are these two classes here. So this one here is not easy to is quite easy to see. It's not difficult. So x1 to the n plus x2 to the n plus xn to the n, we drew a read once planar circuit and it had size like n log n. But any formula must have size omega n square because the individual degree is n. Then there are n variables, each of individual degree n, so the size has to be n squared. Now the other way around is a question you can ask: is there something that can be easily computed by formulas, but any read once planar circuit requires large size? So easy, large, are all very toned down. It's not like polynomials, square polynomials. So you can use super concentrators again, but not as one here. You can use depth two super concentrators to show that there exists an explicit polynomial of degree 4 such that it is computable by a formula of size n to the 1 plus rho of 1, but any read once planar circuit requires size times. This is again a construction, a similar construction, but now we need to start with a depth 2 super concentrator, and we know good constructions of depth 2 super concentrators. So for every n, we know depth 2 super concentrators of size n to the 1 plus rho of 1, and then you do the same trick. SUBT. So this sort of settles that there are different models and there are some separations between these. This mostly
Variant so that what is not explicit, the weight function.
the weight function is not explicit. We don't know how to get an explicit.
So, and the matrix M, so once you have, so the graph is fixed. If you, the super concentrator is fixed, it's just a weight function, so this one. So does that mean in the matrix that you have, you know, you have that these locations should all be zero, and there are some stars and you don't know
What the star?
what
But
the
you
star.
know, over infinite fields, there exists a setting of the stars.
Such that every submatrix, every square matrix is full rank.
The determinant will be.
It's similar to these things. Yeah.
I mean, at the moment, we don't know if there is a way to make this explicit. Try to do it. Okay, so if you looked at the Boolean circuit case, there were also lower bounds for circuits computing multiple functions, not just one Boolean function. A similar situation also arises in the arithmetic circuit. So if you fix M to be any totally regular matrix and consider this linear transformation Mx, so now you are constructing n linear forms, each on n variables, then you can improve the lower bound to n to the 4 by 3. I mean, you can't really say improve because now you are computing n functions, not one function. So naturally this will be. And this sort of immediately tells you, if you have seen the statement by Baur and Strassen, that all the first order partial derivatives of a polynomial can be efficiently computed. Meaning if you have a circuit of size s computing f, then you can construct a circuit that simultaneously computes all the partial derivatives of size order s. So this statement is not true for formulas, which was sort of not well studied. If there is a polynomial that is computable by a small size planar circuit, but small here is n to the 1 plus of 1. But if you try and compute all the first order derivatives simultaneously, then it's omega n to the 4 by 3. So this is used from, this is based on the fact that if you look at y transpose mx, right, and take partial derivatives with respect to the y variables, it's actually m times x, the linear transformation. So you have a lower bound. So there is a lower bound on the partial derivative form. Okay, that's pretty much there. Yes.
Any more questions?
So for example, for something like homogenization in general, is there, I mean, would one expect that that is something that can be done while preserving planarity? Like someone gives you a planar circuit, but compute doing something non-homogeneous. But I want to.
It's similar to bilinearization. BSB
So bilinearization here, it was important that you only had. There were only.
all of this is based on the fact that the original circuit has spanning 2 and fan.
No, and you only needed to keep track of linear and the quadratic terms.
Here you need
But now you need to keep track of D. It's and I see some function of D showing up.
Would it surprise you if the n log n size circuit for GFT was planar? It's an opinion question. But the opinion.
We are used to polls going terribly wrong.
Flip a coin and then answer.
They do better than.
It's obvious to profession, but I mean, is there a particular reason for looking at planar circuits apart from the fact that you studied them or not studied? Like, why not boundary with?
We could, so the starting point is planar. So any tree is planar. Trees have been so well studied, like formulas.
Sure. But then why not, boundary
Boundary
trees or something?
But we don't know, so at the moment it's not clear if you have good separators for boundary. So all of these statements sort of translate if you have a good separator, or whatever good means.
So here, in fact, the only thing you care about is the fact that the underlying whatever graph model has a separator.
Exactly.
So boundary graphs would be okay.
Yes, they have, I think it's a generalization of separators.
Same question which I want to ask, which of in the trivial sense, suppose you wanted the thing not to be on the plane, but put it on the surface of a donut or something, the torus. What is it that you want to separate a theorem over there, or what is it that we want?
Yeah.
Because your bilinearization all works in all of these
Yes,
sort of things. Those things very neatly work.
There's nothing fundamental about planar or plane circuits.
Okay. So, no further questions. Thanks.
Butterfly transform. Generally, one of them you have the planarization, which is efficient.
Really? The butterfly thing? The butterfly thing?
No, it doesn't look anything like planar, but